So, let me continue more or less where I stopped last time. Last time I had to rush things a little at the end, so I will take up things quietly again. What I suggest I do is define general stabilizer codes and then go back to the small example of the 5-qubit code. So the general case goes like this. What are we trying to do? We're trying to correct errors, E. What is an error E? It belongs to this set. So it's a finite set made up of identity x, z, y, tensored in the general case n times if we have n qubits. So n equals 5 in the case of the 5-qubit code. And we'll be trying to correct errors E of small enough weight, like in the classical case. We don't expect to correct all possible error patterns, but we're hoping to be able to correct all error patterns of small enough weight. Okay, so what is the strategy? So call this set of Pauli errors E calligraphic. So to construct a stabilizer code, what do? We find the subgroup S of E, so subgroup of error operators, which is abelian, so an abelian subgroup. Abelian is very important. This abelian subgroup has generators. So we had 4 of them last time. More generally, let's say we have R generators. And we can think of them as making up a matrix that we can call the stabilizer matrix. Sometimes by analogy with the classical case, we call it a parity check matrix. And every such set of generators, M1 through to MR, defines a syndrome function, like in the classical case. So, what is the syndrome of an error E? It's a binary R tuple. It has as many coordinates as there are generators. So say S1, I'll write it as a column vector like in the classical case. S1 through to SR, so this is in 0, 1. To the R. And what is the definition of S1 and more generally SI? Well, it's like this. It looks at whether so SI is either 0 or 1, and we declare it to be 0 if E commutes with MI. And we declare it to be 1 if E does not commute with MI, which means it anti-commutes with MI. Like this. And because E and the MI's all belong to this set of operators, like we said last time, they either commute or anti-commute. There's no other possibility. Okay, to be explicit, last time we had this matrix. So X, Z, Z, X, identity to the 5-qubit code. And 4 cyclic shifts. Like this. So now what is the space of encoded states? The code, if you want, C. So it's the space of states psi that are stabilized by S, such that for any M in the stabilizer group, M stabilizes psi. M applied to psi equals psi. And last time in this particular case, and it's the same definition in the general case, we defined all these other spaces, C of S, to be the set of states phi for which Mi applied to phi equals -1 to the power Si phi. So for all I from 1 through to R. So in particular, for the zero syndrome, this 1 or -1 here is always equal to 1. And this is exactly the code C, the set of encoded states. And we can see what happens when we have an error. So this important remark that we made last time is what happens if we apply Mi to a corrupted encoded state. So psi belongs to the code. E times psi is a corrupted state. What happens if we apply Mi to it? Well, it either commutes or anti-commutes with E, so it gets this factor in front of it, -1 to the power Si E times Mi psi. And by definition of psi, Mi psi is exactly psi. All the Mi, all elements in the stabilizer group, they stabilize encoded states, so this is the same thing as -1 to the Si times E times psi. So what does it mean? It means that E times psi falls into one of those spaces, the C of S. And the little miracle is this. So the theorem, our whole ambient Hilbert space, so h to the power n, decomposes as an orthogonal direct sum of the SI, of the C of S. For all S, okay, my notation is not very good. No, it's okay, never mind. For all S in the set of syndrome values, so in 0, 1 to the R. So what does it mean? It means that we can measure the syndrome of the error. We have a measurement which will project on the C of S, and if the state that we're measuring is E times psi, well, the measurement is going to tell us exactly E times psi is in some C of S, where S is the syndrome of E. So the important consequence is that this gives the syndrome of E if the measurement is applied to E times psi. Okay, hopefully this is good enough. And the goal of decoding now is to recover E from the syndrome of E. And then, once we have E, we can apply it again to E times psi. But E squared is the identity. So we recover the original encoded state, psi. So why do we have this orthogonal decomposition? I said this quickly last time, I'll say it again, is because what are the states, what are the spaces C of S? So we see that phi that is in C of S is an eigenspace of the operator mi. Also notice that mi squared is equal to the identity. So its eigenvalues are either 1 or minus 1. So we have two eigenspaces. And what we're defining is an intersection of eigenspaces. Some eigenspaces correspond to the 1 eigenvalue of some mi, some correspond to the minus 1 eigenvalue, and we intersect all these eigenspaces. And now, why is it important, why is it absolutely fundamental that we have commuting operators mi? Because it means that they can be diagonalized in the very same basis. So in the right basis, mi will look something like this if you want. It will be diagonal with a bunch of 1s, a bunch of minus 1s, and m2 will look something like this. So some ones, some minus ones, some ones again, some minus ones, and here we will have a basis for one of the C of S in the case of two generators, and this can be applied to any number of generators of the stabilizer group. So this is why all the C of S are orthogonal and form a orthogonal direct sum decomposition of the whole Hilbert space. So going back to the example of the 5-qubit code, we can compute a couple of syndrome examples. So, for example, consider the error pattern E1, which would be X on the first qubit and ones or identities on the other qubit. So what is the syndrome of E1? Well, we applied to those four operators, so we see that E1 commutes with the first generator on the first qubit because X commutes with X. It commutes with the second generator because X commutes with identity. It commutes with the third generator, and it anti-commutes with the fourth generator because X anti-commutes with Z. So we get 0, 0, 0, 1. We can do E2 equals Z, 1, 1, 1, 1. This time, syndrome of E2 will be equal to 1 because Z here anti-commutes with the first X in the first row. Then there's an identity, 0. Then the 1 because there's an X again, and 0 because Z commutes with Z. Let me do last one. E3, suppose E3 is Y, identity, identity, identity. Syndrome of E3 will look like this. Y anti-commutes with X, also with Z. And we get this 1, 0, 1, 1. And you can notice that all these syndromes are different. And I'm not going to go through all 15 error patterns with weight 1. So what do I mean by weight 1? I mean error patterns that have only one component not equal to identity. So these three patterns are of weight 1. There are 4 identities and something else. Okay, so 5 coordinate positions, 3 ways of putting non-identity symbols, 5 times 3, 15 error patterns. And a little miracle happens. They all have different syndromes. It's a little miracle because you only have 15 non-zero syndrome values because 0, 1 to the 4, that's the space of syndrome, has size 2 to the 4, 16. If you take away the zero syndrome value, which corresponds to the all identity error pattern, then we only have 15 values left. Yes?
But this works specifically because the N1, 2, 3, 4 have been chosen this way, no?
Yes, exactly.
Okay.
These are very special, that's a very special choice of generators that magically works. Yes?
I don't understand the theorem, why the sum of the CS span the subspace. For instance, if you take C0,
Yes?
why isn't it the empty subspace, zero subspace? Because if in the diagonalization of the ones
So, C,
are in different places, then the space will be the zero space. And I don't understand why you do.
okay, why is C0 not the zero subspace? Why is this direct sum decomposition non-trivial? So something that I've been quiet about is what are the dimensions of the subspaces C of S, and this is really what you're asking. So you should agree with me that we do have a direct sum decomposition because we have intersections of eigenspaces that are all described by the same orthogonal basis. What is not completely clear, possibly, is what are the dimensions of the C of S? So maybe if we're unlucky, the dimension of C0, the code, is 0. So that requires a slightly tedious linear algebra, symplectic algebra proof, which is not especially difficult, but it's true. All the spaces C of S have the same dimension. In particular, for the code, what happens if you take the one eigenvalue, one eigenspace of the first generator, it will have dimension n over 2. So the one eigenspace and the minus one eigenspace of these Pauli operators, they have the same dimension. So in this example, 16. So if we choose the one eigenspace of the first generator, we'll get a space of dimension 16. We intersect it with the one eigenspace of the second generator, we'll get dimension 8. We intersect it with the third generator, we'll get dimension 4. If we intersect it with the fourth generator, the one eigenspace of the fourth generator, we will get dimension 2. It needs a proof. If I start proving it, I will not have much time to talk about anything else, so just trust me on this. It is not a super complicated proof. There are no fancy ideas in it. It's really standard linear algebra. You just have to look a little more your generators in the eye, so to speak, so as to understand how these plus one and minus one eigenspaces distribute themselves. Yes?
So can the code also correct larger distance errors? And if so, can one quantify or identify which ones it can correct?
Yes. so in the case of the 5-qubit code, we can understand everything. The general case can be somewhat mysterious. It depends on the code. I will be addressing this question exactly a little later, so allow me not to give an answer immediately, but I hope that in the course of the next half hour you will get answers to this question, and if not, you can ask it again. Right, so you can continue this little exercise with the 15 error patterns of weight 1, and you will see that they're all different. They span all possible non-zero syndrome values. So if our quantum states gets hit by an error that is good enough to have only weight 1, we will compute the syndrome of the error by doing this measurement, and we will know exactly what the error is, and we can apply it to the state again and recover our initial state. At this stage, you might want to protest, like I said last time, and say, okay, this is very nice, this is a very cute mathematical object, but why should we have errors that are only X and Z and Y errors? Surely in the real world we'll get something more general than this. Our quantum states will be moved about in a more general way. Yes, but this is the sort of thing that happens. So real world errors. What will they look like? So let me just describe one on 1 qubit. On 1 qubit, theory says that your qubit is going to be hit by a unitary operator. And in dimension 2, there are really no choices. Any operator can be written as a combination of identity, an X operator, a Z operator, and a Y operator. And now, suppose for a moment that your first qubit, instead of being hit just by an X or a Z or a Y, it gets hit by a combination of them. So we will have U tensor identity, tensor identity, tensor identity, tensor identity, psi. So this decomposes into alpha psi. This beta x1 1 psi plus gamma z 1 1 1 psi, using little shorthand plus delta y identity psi. And now you see that the first term belongs to the set of encoded states. The second term, it belongs to C of some value of S, of syndrome of the first error pattern. And I'm not writing it explicitly so as not to make a mess on the blackboard, but you see what happens. Every one of these terms falls into a different C of S. So what is our measurement? Now, we apply our very same syndrome measurement. What is it going to do? What is it going to do? It's going to choose one of the C of S. It's going to choose one of those components. And what does it mean? It means that we will end up in exactly the same situation that we would end up in if the original error were a pure X error, a pure Z error, or a pure Y error, or maybe no error at all. That's reasonable. So one way of thinking about this is that the syndrome measurement, it basically transforms the real world error into a pure identity X, Z, or Y error. And this is why it's enough to devise schemes that will correct errors of this form as opposed to very general errors. I've cheated very slightly, but not very much. I've just considered the case where we have a general error on the first qubit and nothing on the other qubits. The real world, once again, we will have general errors spread out all over our qubits. We can't hope for qubits to be left alone. But we may decompose our state in the very same way over all the CES. We'll get slightly more messy components, but we'll get a dominating component which will, again, correspond to a very specific error, meaning that up to small noise values that I don't want to delve into, basically everything will happen as if we had a pure identity X, Z, or Y error. Okay. Code parameters. So, like in the classical case, the number of physical qubits that we're dealing with is usually denoted by n. We call it the length of the code. Another parameter is the dimension. Here things change a little. So what happens is that the dimension of C0, our set of encoded states, well, as I said before, it starts by 2 to the n, and every time we add the generator, we divide the dimension of the Hilbert space by 2. Again, I'm not formally proving this for lack of time. It's not a hugely difficult thing to do. And this means that you want to think of the number of qubits that you're encoding as living in a space of dimension n minus r. So the number of logical qubits is n minus r, and we call this k n minus r. the dimension of the quantum code. Which kind of corresponds to the classical case. Typically in the classical case, you have R parity checks for your classical code, and the dimension of the code is n length minus the redundancy R. I'm calling it R because redundancy. N minus R is the dimension if you put linearly independent rows in your parity check matrix. And now the third parameter in the classical case was the minimum distance of the code. Here we again define the distance parameter. So if you remember what it was in the classical case, it was the smallest weight of an error pattern with zero syndrome. So we attempted to say this. It will be the smallest weight of E, so by weight I mean the non-identity terms in our Pauli error. The smallest weight of error E such that sigma E is equal to 0, but here there's a twist. A small but significant difference with the classical case. That was the definition in the classical case. And here I'm going to add smallest weight of E that doesn't belong to the stabilizer group of errors. Because by definition, our stabilizers, for example, our generators here, well, they stabilize the quantum state and they have zero syndrome. But they stabilize the quantum state. So if we have an error with zero syndrome that stabilizes the quantum state, well, we don't really care about such an error if, okay, M belongs to S. By definition of our encoded states, applied to psi, it's just psi. We don't care if an error like this occurs, because we don't need to correct anything. It doesn't change the quantum state. But we will be in trouble if an error of zero syndrome is applied to the quantum state, because we'll get a zero syndrome and we will think that nothing has happened, possibly, but something really bad has happened. We will be outside our original space of encoded states. So for example, the 5-qubit example, we could have XX identity, Z identity, and you can check that it commutes with all 4 generators. So for example, with the first generator, we'll have exactly 2 coordinates, the second and the fourth, where an X and a Z meet, but you have 2 of them, so individually the operator's restricted to that coordinate n to commute, but globally they commute because you have an even number of them. But you could also check that this doesn't belong to the stabilizer group. And this is the smallest weight you can get in the case of the in the case of the 5-qubit code. So the 5-qubit code has a minimum distance equal to 3. So the parameters of a quantum stabilizer code are usually written like this, N, K, D, like in the classical case. Yes?
I believe with the 9, we thought this happens, so this is not a problem. Maybe you want to put the normalizer first here.
What is not? Yes, you can formulate it exactly.
There is some an error which is a net, but it's not a true problem.
Yes, so that always happens with stabilizer code. If you have an error which is in S, it's never a problem. By construction, it doesn't change the quantum state. So we have nothing to do with when such an error happens. So this is a strong difference with the classical case. In the classical case, when you have a non-zero error, it always is bad. I mean, it changes your original code word into something you don't want. But in the quantum case, you have this new fact that some non-trivial, some non-zero errors, some non-identity errors, if you want, may occur that don't bother us at all. They don't change the quantum state. Okay. No. No. Sorry. Okay. In practice, these general stabilizer codes can be pretty challenging to construct. Okay, 5 qubits, you can kind of explore everything there is to explore and find this code, figure out which are the best. But if you want codes for large M, then you need some mathematical tools and methods, and they're difficult to devise in the general case. So the codes that we look for are usually a subclass of the class of stabilizer codes. We usually focus on CSS codes. So CSS codes were discovered independently by Carl de Bank and Peter Shaw. That's the first 2 letters. And there's an independent paper by Steen, who's the co-discoverer. And what are CSS codes? They're codes for which you can find 2 sets of generators. So they're stabilizer codes. They can be described with the set of generators of a stabilizer group. But the special thing that happens is that we have a set of generators which have only x's and a set of generators that have only z's. X generators, Z generators. That's it. That's a CSS code. Their sets of generators are kind of easier to deal with, to devise, than the general format of a stabilizer code. So, to take a small example, the Steam code. How is it constructed? It's constructed from the classical Hamming code. If you remember from last time, we gave the example of the Hamming code of length 7, which has this parity check matrix, which is constructed by taking all possible columns of length 3, non-zero columns of length 3, there's 7 of them. And if you look closely at this code, you can see that the support of code words here, they meet in an even number of positions. So these rows, they generate the self-dual classical binary code. So self-dual, or if you prefer self-orthogonal, actually self-orthogonal is better terminology. Binary code. So for the inner product over F2, it just means this. I mean, orthogonal binary vectors, they're vectors whose supports meet in an even number of positions. That's it. So what can you do? You can do this. You can transform this matrix into a set of X generators. How? Every time there's a 1, you put an X. Every time there's a 0, you put an identity. That's it. That's a bunch of X generators. And you need also Z generators. And in this particular case, which are you going to choose use the very same transformation. So Z, 1, 1, 1, Z, 1. And if you're not completely convinced, you can check that any row of Hz and any row of Hx together, they meet in an even number of positions, meaning there's an even number of positions in which you have X and Z, which means that any generator here commutes with every generator here. So in this way, if we take all 6 generators, we've created, they generate an abelian group, which is what you want to define a stabilizer group. Okay, this is the Steen code, and you can check that it has these parameters. Length 7, obviously. dimension is 7 minus 6, because 6 generators, so 1. And I'll leave you to convince yourselves that the minimum distance is 3. This code can also correct single errors, any error of weight 1, like the 5-qubit code. So the 5-qubit code is the smallest code, the smallest stabilizer code that can correct 1 error. You need at least 5 qubits to correct 1 error. The Steen code is the smallest CSS code that can correct 1 error. It needs 7 qubits. So CSS codes maybe in pure parameter terms, they may be worse than stabilizer codes. You can improve upon CSS codes with more general stabilizer codes, as the Steen code and the 5-qubit code examples show. But one can also show that asymptotically you do not lose all that much. If you have very long stabilizer code with some parameters, you can transform it into CSS codes with slightly worse parameters, but not catastrophically worse parameters. I will not explain how. Okay, so what is especially nice about CSS codes, especially if you come from classical coding theory, is that they can be described by pure binary matrices, 0, 1 matrices. So you need 2 matrices, one matrices, one matrix, let's call it HX, that will look like this, but it has only 2 types of symbols, so you could describe it in pure binary form, 0, 1 form, and also the HZ matrix, you can also describe it in binary form. So all have elements in F2. And how does the commutativity condition translate? So X operators will always commute with X operators, Z operators will always commute with Z operators. The tricky part is that X operators may, if we're unlucky, not commute with Z operators. So you need to be careful how you choose your 2 matrices. The property that you need is that every row of HX should be orthogonal in the binary sense to rows of HZ. Any pair of rows, one in HX, one in HZ, should be orthogonal. Orthogonal just means their supports meet in an even number of positions. So, next, you want to construct good codes. How do you do this? So, in practice, if one may use this term, for quantum computing applications, engineers tell us we need LDPC codes. So it just means that we want our matrices H and X, HX and HZ, to be sparse, to have a low density, meaning a low density of ones. We want an upper bound on the number of ones per row, and upper bounds on the number of ones per column, typically. Why? Because the syndrome measurements, so we've seen the key to quantum error correction is measuring syndromes. This is a quantum measurement. It's something non-trivial, it's something tricky, and if you're measuring a syndrome corresponding to some generator, to some parity check equation of low weight, it means that you only have to look simultaneously at a small number of entangled qubits, the ones that have an X or a Z in their positions. So the operator that you're measuring, if you want, involves a small number of qubits. If it involves too many qubits, engineers tell us this is going to be hopeless. We don't want to do this. The measurement will be too unreliable. We need your quantum codes to be LDPC. So how do we do this? So we could try to make them as sparse as possible. So as sparse as possible basically means we will limit ourselves to 2 ones per column. So 2 ones per column for HX, 2 ones per columns for HZ. And a certain number of ones for rows. So, for example, we could try and do 4. So, remember, if we're only looking at HX, 2 ones per column means that we're looking at the incidence matrix of some graph, and same thing for HZ. If for a moment we go back to the maybe yellow X and Z notation, and we look at a column, how can we view a column? If we only look at one of the 2 matrices, as we've said before, we can think of it as the edge of some graph. But if we look at both together, we have 4 points. So 4 vertices, 2 vertices here and 2 vertices here. And if I draw edges between an X vertex and a Z vertex, I will get a square. So another way of looking at things is that our two matrices here, they're really describing what is called a square complex. It's a two-dimensional geometric object, which is a graph, if you want, but which is full of squares. We really have a square complex, two objects, three sets of objects, vertices, edges, and now squares. I will not say that much more about this point of view for lack of time, but this has led to powerful ways of looking at things and devising quantum code. So the mother of all quantum LDPC code is Gitaev's Tori code that you've already been exposed to, I think, in different contexts, so let me define it again from a coding theory point of view. 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So consider timing of a torus. It means a grid like this, and you create a nice 4 regular graph by identifying the two top edges of the square, which kind of looks like a rectangle in my case, but never mind, and the two vertical outer edges of my square. So you think of it like this, and you have this nice 4 regular graph. And there are several ways. So we have this graph, a vertex set and an edge set. And actually it's also not only a graph but a square complex, but let me not focus on this too much at the moment. So the traditional way of presenting the Gitaev code is putting the qubits, or just the bits if you're thinking in classical terms, on the edges. So our end in space is f2 to the e. And how do we create our two sets of matrices, hx and hz? So hx will be like this. Each row will correspond to elementary co-cycles, so there will be one row for every vertex in the grid, like this, and all the others will be 0. And so on. And for hz, we will use the squares instead. So we'll put rows supported by every little square. And now you can see that every row of hx will be orthogonal to every row of hz. Either the supports don't meet, or if they do meet, they meet in exactly 2 edges that form a little corner. So they're orthogonal. Again, it means that if you transform them into a set of x operators and z operators, they all commute. And now, the syndrome function that we defined before, it translates into really 2 syndrome functions, one for the hx matrix and one for the hz matrix. And the minimum distance it's given by smallest error pattern with a zero syndrome either for hx or for hz. So let me focus on hx. Now, hx, the way it's defined, it's nothing but the cycle code of this graph. It's a parity check matrix for the cycle code of this graph, the one that we defined before. So in classical terms, code words are just cycles of the graph. They're the ones with zero symbols. But now we have cycles that from the quantum point of view are trivial and non-trivial cycles. The trivial cycles, they're the ones that are generators of our stabilizer group. So every cycle that is a yellow cycle here, that is an elementary cycle of our tiling, or a sum of elementary cycles, squares if you prefer. It's a trivial cycle, it stabilizes our quantum states. Yes?
What is the cycle in the suite? Like you go left, right, up and down, like you do a return? Like what's another cycle?
Okay, so you can think of cycles in a computer science sort of way. You start from a vertex and you move along edges until you go back to your...
Is it like can your cycle do some loops and cross itself? Can your cycle go back and forth?
Yes. So the point of view that I'm using is really the homological definition of a cycle. I don't care about where I start, where I finish. I don't care about the dynamics, if you want, trajectories. What I want is a set of edges. That's all I want. And the definition of a cycle, in the sense, it's a set of edges with the property that every vertex meets this set of edges in an even set of points. And if you have this, then it's not difficult to convince yourself that you can move along the cycle, start somewhere and go back to where you started. Because the even property means that when you arrive somewhere, you can always leave it. This homological definition generalizes to more abstract objects. That's why it's interesting. So the non-trivial cycles are the cycles of the graph that are not sums of squares. And these look like this. They're cycles that wrap around the torus. And you can convince yourself that a cycle that does this, you can't express it as a sum of squares. For example, because vertically in this row, this edge appears only once, and every time you use a square, you have a parity issue. You use two vertical edges, for example. And also vertically. So one can compute the dimension, the parameters of the code. So if you use the length, okay, m, for your grid, the number of edges will be 2m squared. The dimension of your code, it's not too difficult to convince yourself that it's 2, so one dimension for the vertical direction, one for the horizontal direction, and the minimum distance is that of those loops that wrap around the torus. which is M. I haven't mentioned how to treat HZ, but it can be treated in a similar way. Actually, there's a one-to-one correspondence between elementary cycles, elementary co-cycles. If you use the dual tiling, squares becomes crosses and crosses become squares. I don't want to be more specific than this. There are many ways of using and representing the Kitaev code. Another way, which is possibly slightly better, and I hope will not be too confusing. Remove the colors. Take this very same grid, but this time put the bits or the qubits on the squares. And now we will have two types. The vertices, say yellow and red. And yellow, say, will be for the Z matrix, and red for the X matrix. And now we use the square neighborhood of every vertex to define a parity check equation, a row of HX. So this vertex here, say call it A, it corresponds to now to a row of HX, which is row A, and we have ones in the positions corresponding to the squares adjacent to A. And we do the same thing. The yellow vertices that get the Z checks. And you can see that when two checks meet, they meet in two squares, two positions. And this time the definition is completely symmetric. You can see that the role of HX and HZ are exactly the same. There's an even odd issue for the wrapping around to work. You're going to need M to be of the right parity, which is not the way I've drawn things. So you'll need something like this so that you can identify red vertices with red vertices. And now you get parameters which look like this, m squared 2m. So minimum distance, which is exactly the square root of the length. Okay, the Kitaev code is the most studied LDPC code, quantum LDPC codes. There are a huge number of papers about it, about how to decode it. So I don't have time to properly address decoding issues. One of the things you can do is use generic decoding algorithms for cycle codes of graphs, and I've mentioned briefly last time that cycle codes of graphs can be completely decoded. We have complete decoding algorithms for cycle codes of graphs that are polynomial time. And this is something truly exceptional. One can apply this. In the quantum case, it's not quite good enough because this generic decoding algorithm is polynomial time, but it's not linear time. And in the quantum setting, we want decoding algorithms that are super fast because we don't want to wait too long for our quantum states to get corrupted. So remember, the strategy for decoding is doing a syndrome measurement and then use a classical computation to figure out what is the error vector from its syndrome value, and then we immediately apply the error pattern that we've found to the quantum state to hopefully get it back into the initial state. But we want to do this quickly, so figuring out what is the error pattern from its syndrome, in other words, decoding, and the decoding problem is close to a classical decoding problem. We want to find ways to execute this really, really quickly. So decoding Kitaev code has been pretty much optimized these days. It's still not completely clear what is the best way to decode the Kitaev code. There are a number of options available to us. I'm not going to say any more about this. In my last 10 minutes, maybe a few words on recent developments. What can we do to create alternatives to the Kitaev code? So what are the drawbacks of the Kitaev code? It has a small dimension. So we pay a heavy price. We encode only 2 logical qubits into potentially a large number of qubits. Also, its minimum distance is not bad. It's square root of the length. But we may hope for larger minimum distances compared to the length. Until a few years ago, this was a super challenging problem. We didn't know how to get a minimum distance for a quantum LDPC code larger than the square root of the length. We knew of a construction that gave something marginally larger than the square root of the length, which goes back to maybe I won't write them down, Friedman, Meyer, Luhr. And this code also had dimension 2, and the minimum distance, instead of being square root of n, it was square root of n times 4th root of log n, a small term. Fiendishly difficult construction involving some tilings of a 4-dimensional object. And that was it. Until the first years of this decade, we didn't know how to do better. And then there were a flurry of results improving on the minimum distance. So a few ideas that one could apply. One thing that you could look for is improve the dimension. So to improve the dimension, you might want to stay with columns of weight 2 and have larger weights, for example, weight 5 for your row weights. If you manage to do this, then you will get a dimension which grows linearly with n. So you can do this sort of thing with geometry. Actually, this is the only way of doing this sort of thing. If you apply this square complex point of view that I briefly mentioned, you could do something like this. So here's a vertex. So you can construct some tiling which would locally look something like this. So attach to every vertex 5 squares instead of 4 squares, like this. And you want to continue in this way, and I'm not going to risk drawing much more. So you get something that you can't draw regularly on a Euclidean plane, but you can make this into a nice regular tiling with a hyperbolic distance in the hyperbolic plane. And find ways of taking finite quotients, so you have to do something more complicated than for a torus. If you want to grow this picture and somehow attach the boundaries so as to create a nice regular 5 regular graphs. I will not go into how you can do this. You can do this with algebraic and geometric ideas. You get interesting codes like this with a large dimension. Unfortunately, minimum distance is not going to be very good. It can't grow faster than a log of n. And then you have product constructions, something called the hypergraph. Product construction, hypergraph, product codes. And I'm going to be out of time, so I can't describe the construction completely because I'm out of time. So these codes, they try to go from 2 1s per column to more than 2 1s per column, say 3 1s per column. And the idea is to use some product construction. If you think of it, the Kitaev code is the underlying object, the grid, it's a product of 2 graphs. It's a product of 2 cycles. So we might want to try and do the same sort of thing by using products of more complicated graphs or even of hypergraphs. Why we should go to hypergraphs rather than graphs, I don't have time to delve into it, but this gave a significant improvement in the sense that we could have a dimension which scales linearly with the length and keep the minimum distance at least square root of n. And then the recent developments, they transformed this product construction idea. The idea was to add lifts to the construction. There's this groundbreaking paper called fiber bundle codes. The idea is to use fiber products rather than ordinary products. I don't have time to tell you how that works exactly. It's kind of involved. And finally, that would be conclusion. In 2022, we had a Panteleev Kalanchow construction that achieve a minimum distance that grows linearly with n LDPC codes, and also a dimension that grows linearly with n. There's a variant of this construction by Le Verrier and yours truly, which kind of simplifies it and uses as one of the ingredients is to use this square complex approach. It replaces this lifted product idea by using well-chosen square complexes together with some ideas from classical coding theory that, again, I don't really have enough time to talk about. But this gives you a brief glimpse into the world of quantum LDPC coding, which is an area that is moving very much, both from the theoretical point of view and from the practical point of view of constructing good, relatively short length quantum LDPC codes. Decoding them is also the challenge of the moment, as well as some other challengings, which are decoding when your syndrome measurement is not entirely reliable. These are the very hot topics that people are looking at.
Thank you, Gilles.
Take any more time. Thank you.
Is there some questions? Yes.
I had a question. All of this was to encode 1 qubit. How do you apply a gate to this qubit, and how do you connect it with other qubits?
Okay, there's kind of more than one question. So, yeah, you really ideally want codes that encode more than 1 qubit. So the 5-qubit code that we've discussed at length, it encodes 1 qubit. The Steen code that we've briefly discussed, it also encodes 1 qubit. The Kitaev code, and this is one of its real drawbacks, it encodes 2 qubits, not more. So if you're going to use the Kitaev code, it implies using a lot of resources for error correction. Now, what I was saying quickly at the end is that some of the improvements that came after the Kitaev code was to find ways of constructing codes with a dimension that grows with n, that grows linearly with n. So if you move to tilings of the hyperbolic plane as opposed to tiling of the Euclidean plane, you'll get something which resembles in spirit the Kitaev code. You can define it in very much the same way, but the grid is different, and because the grid is slightly different, if you put a degree 5 here instead of a degree 4, then the number of generators that you have in HX and HZ, they're not close to n, the total number of qubits anymore, and you end up with a dimension which grows linearly with n. Also, in the other constructions that I've briefly mentioned, you encode much more than 1 qubit. And
the question was more, how do you apply gates on this code?
yeah, so this is ongoing research. So strictly speaking, quantum LDPC codes in the basic format, they protect quantum memories, if you want, as opposed to quantum circuit. They protect quantum states. The next step is to devise a way to compute with encoded states. and that's a whole topic. It's fault-tolerant computation. It's a totally non-trivial question. I can't begin to answer it properly.
Thank you. Another question?
In the course that you showed, it looks a bit, it's planar always, and does it mean that in terms of hardware you need only local connectivity, and is it still true for the new constructions?
If you go to tilings of the hyperbolic plane, yeah, you can't make it properly planar in a Euclidean plane. That's not going to work. So yeah, you're going to have to deal with connections that are not purely local. New technologies, when photonics were the main technology, this was a huge issue. People thought, we're not going to use other codes than the Kitaev code because we can't deal with this non-locality, non-planarity. But with cold atoms technologies and a few others, people say that long-distance interaction is not such a big deal anymore. So yeah, we very probably don't have to stick with Kitaev codes.
So thank you. I propose to left all the questions directly to Gilles during the lunch, since we have to join the restaurant now. So thank you again, Gilles.
Thank
and
you.
See you this afternoon.